Hello and welcome back to our series on abstract algebra. In the last video, we took a look at some examples of rings and how they all satisfied the axioms of rings. Those examples that we looked at were all infinite rings. Okay, today we're going to lay some of the groundwork for talking about some of the important finite rings. Okay, rings with only a finite number of elements. So now you may be thinking, if we have a finite ring, how do we deal with the issue of closure under addition and multiplication? So here's a simple example. In this set, I have the elements 0 and 1, the integers 0 and 1. Okay, well, it doesn't take too long to realize that this will not be closed under addition. If I add 1 plus 1, I get 2. And that's a big problem because 2 is not in my set. Okay, so that means this set of integers does not constitute a ring, right? It violates the closure under addition. Now, what if we just did a bit of a thought experiment, okay, and we just sort of temporarily forgot about the rules of addition, and what if we just sort of stipulated that 1 plus 1 equals 0, okay? Now, when I do this, a lot of you will probably object, but just humor me for a moment. If we do this, we do actually solve our problem of closure for addition. Now it's closed, right? 0 plus anything will always be 0, and if I add 1 to 1, I get 0, so we're good, right? 0 plus 1 will still be 1. So I can no longer escape this ring, or this set, through addition. If I make this change, then this set actually does constitute a ring. You can check to see that all of the other axioms that we've talked about are satisfied. Okay. Now, obviously, I can't just do this without some justification, right? When I've changed this here, when I just write 1 plus 1 equals 0, what I've actually done is I've actually changed this set from being a set of integers to a set of something else, a set of objects called congruence classes. Okay, now we'll talk a little bit more about what exactly those are and how they're defined and how they're structured in part 2. But for now, I want to focus on a bit of intuition, right? Why would you want to do this? Why would you want to have a number system where 1 plus 1 equals 0? Okay, so here's a very simple example. Okay, suppose you want to find out how many unpaired socks you have, okay? Well, if I just have one sock, the answer is 1. I have one unpaired sock. But if I add another unpaired sock to it, all of a sudden, I have 0 unpaired socks. All right? So here we have a situation where functionally, right, in terms of what we're interested in, namely unpaired socks, 1 plus 1 equals 0. They cancel out to give us nothing, right? If I add a third sock, right, then I have 1 unpaired sock again. If I add another unpaired sock, now I have 0 again. And you might object by saying that these are not actually a pair, but that doesn't matter. We're just talking about numbers of socks, and these would do well enough. Okay, so you see how we have created a number system where it actually makes sense to talk about 1 plus 1 equaling 0. Okay, this is one of the simplest finite ring that we could think of. This is one of the simplest examples of doing this. Okay, there are other examples too. Imagine that you have a clock with military time, right? Okay, so you start at 24, right? 2400 hours, and you owe 100 hours. That would just be 1 in the morning. 1300 hours would be 1 p.m., right? 1 in the afternoon. Okay, and then if you had a system like that, say we're starting at 1 in the afternoon, so we're starting with 13. What happens if I add 24 hours to that? If I wait a 24-hour period, what time am I left with at the end of it? Well, the answer is I'm still left with 13, okay? What that means is, in this number system, in our military time number system, the number 24 is 0. It's functioning the same way that 0 does. I add it to 13 and I get 13. Okay, so that set, I'll write it over here actually. I'm not going to list all 24 elements, okay, but it would start with 0, and then 1, and then 2, so on and so forth. And then the last two would be 22 and 23. Right, because remember when we get to 24, that's just back at the beginning, that's 0 again. Okay, so the last element in this set would be 23. And equipped with this rule, right, with this idea of arithmetic, where you just sort of cycle back, so this is a ring, okay? So now that we've established that these two are rings, by the way, this ring here, this ring with two elements, 0 and 1, this is known as Z2, okay? And this one is Z24, right? So this one has 24 elements in it, and this one has 2. That's just how they're often denoted. If we have a ring like this, say Z24 as our example, how does arithmetic work in this ring? Well, if you are working, so long as you never obtain a number bigger than 24, it works just the way it would in the integers, right? 3 plus 5 would equal 8, right? Okay, so if you're starting at 0300 hours and you wait 5 hours, you're going to get to 0800 hours, right? So that's just normal addition, right? The times where it changes are when you get bigger than 23, essentially, right? Because if we get up to 24, 24 is 0 again, right? The element 24 is our additive identity. It's our 0 element in this ring, and I've just relabeled it as 0, essentially. So, for instance, if I have something like 15 plus 10, well, this is saying we're starting at 1500 hours, which would be 3 p.m., right, 3 in the afternoon, and I wait 10 more hours, well, I'm going to get to, 25, okay, but this is really equal to 1, right? Because I'm essentially, I get up to 24, which is 0, and then I have 1 left over, which is 1. Okay, if I start with 22, and then I wait 7 hours, so I'm adding 7, okay, then I'd get 29, just adding as integers, but 29, at this point I've gotten to 24, and then there are 5 left over. So this is really equal to 5. So basically, every element is equal to the remainder that you would get, okay, if you divided this number by 24, right? If I divide 29 by 24, I get a remainder of 5. If I divide 25 by 24, I get a remainder of 1. If I divide 24 by 24, I get a remainder of 0. So it works with that as well. Okay, and it's the same thing with multiplication, right? If I start at 0, so 12 at night, right? I start at 0, and I wait, 6 5-hour periods of time, right? Okay, so we're bringing multiplication into this. 6 times 5. Well, in normal integer multiplication, this equals 30. But in our arithmetic here, if I divide 30 by 24, I'm going to get a remainder of 6. This is equal to 6. All right? And note, too, if I divide something like 2 by 24, 24 goes in 0 times with a remainder of 2. Right? So that rule works for all of the elements which are less than 24 as well. Okay. And just as another quick example here, say we take the ring Z7, okay? So this has the elements 0, 1, 2, 3, all the way up to 6. Okay, so again, my elements are all of the possible remainders when I divide by 7. If I divide a number by 7, I can only get one of these 7 numbers as a remainder, okay? And this one can be useful in real life for describing days of the week, right? Because there are 7 days of the week. If I let Sunday be 0, and Monday be 1, and Tuesday be 2, and so on and so forth, right? Then you can answer these sort of brain teaser questions that you might see in puzzle books or something, right? If it's Monday today, and you wait 150 days, what day will it be, right? Well, we could set up 1 plus 150, okay, right? Because we're starting with Monday, and we want to know what day will it be 150 days from now. But now 150, if you divide 150 by 7, you'll actually get a remainder of 3. Okay, you can try this using long division at home. I'm not going to do it here. But what that means is this is really equal to 1 plus 3, which gives us 4 here. Okay, so Sunday, Monday, Tuesday, Wednesday, Thursday. The answer is it's going to be a Thursday. If you're on a Monday and you wait 150 days, you will land on a Thursday. So these are just some examples. Obviously, we could have any number here that we wanted. I just picked 3 that had nice intuitive examples. And like I said, when we're dealing with rings like this, these elements here are not really the same thing as the integers that you're used to dealing with. They're really objects called congruence classes. Okay, so in the next video, we're going to look at congruence in more detail. We're going to look at a more rigorous mathematical underpinning for these objects, and we'll take a look and see that they do satisfy all of the criteria for being a ring, not just closure under addition and multiplication. Thank you for watching, and we'll see you next time.